here we are. Hi, everyone. Thank you for coming. Yes, I'm going to talk today about You Can't Handle the Root, container isolation for secure multi-tenancy. So a little bit about me. My name is Marina. I'm a research scientist at Adara, a company that builds kind of a hearted runtime for containers. I'm, as Ray mentioned, the co-chair of CNCF TAG, the newly renamed TAG Security and Compliance, and I do various other things in open source maintenance. So let's get into it. So as I'm sure most of you at KCDSF are familiar with, a container is a way to, a way to package up your application and all of its files so that it can run in any environment, right? And there's a lot of advantages to this. It's very portable, it can run on any machine, it's lightweight, and so you don't have to have all this overhead to do that. And you can just kind of package, and it's a kind of a universal format, right? There's all these different tooling that's been built around this idea of a container for deploying and using code. And because containers are so useful, a lot of people like to use multiple different containers on the same system, especially in this multi-tenant way, where the different containers have either different companies running on the same system, or different customers of the same company having different copies of a container running their version of the application. And this is great because you can buy one computer and have a ton of different containers running on it. You as a company don't need to buy the whole computer, right? You can get time on a computer and all that stuff. And this is great. But unfortunately, the containers are all, they're sharing the same operating system kernel, and this is just like, a software level abstraction on top of that kernel that makes it look like you have your own view, but actually underlying, you're sharing the same system memory, sharing the same operating system, and so if you have a bad actor in one of these containers, right, there are things they can do if there's no isolation, right, to access the other containers. And if there's anything sensitive or other customer data, stuff like that, you really don't want people accessing those other containers, or even like your underlying operating system, right? These can get really bad when it goes wrong. So what we want is container isolation, some sort of boundary around our containers that protects them, right? That keeps the data and the stuff going on in the container safe. And also, if you have a malicious container, right? Say you're running containers from other people on your infrastructure, you don't know what they're running on your infrastructure, right? You want to keep that nicely contained in this box, right? Make sure it can't escape and affect your infrastructure. And why is this important? As I'm sure most of you know, sometimes it goes wrong, right? And I won't go into lots of detail here, but there have been times when things like the file system has been exposed, or the different privileges have been subverted to cause what's called a container escape or privilege escalation attack. And this is a number of examples from the past year or so when this has happened. So what we want, all this just to say, not to call out those particular attacks or anything, but this is a real problem. And this is the real reason that we need this isolation boundary around our containers. Because despite the name, the container doesn't really contain the application. It's more of like more of an abstraction than it is a security boundary, right, on its own. So I'm going to categorize the different isolation mechanisms that are out there into 4 different categories, which I think is kind of a useful way of thinking about the different approaches to this problem. So the first is application and service isolation. This is things like namespaces, things that operate kind of within the operating system to make it more like its own little box as promised. There's runtime isolation, things that go kind of one step down, use something like a hypervisor to really keep the runtime separate. There's node isolation, which is more of like an architecture design to keep things isolated, and hardware and physical isolation, which is things like confidential computing or like hardware level boundaries between things. And when talking about these, I think it's really important, especially as someone with a security background, to always remember that security is not the only thing that all of you care about, right? You have a lot of other things going on in your lives. You care about the performance of your applications, right? You want to make sure that they can actually run, they can maintain all the performance that folks expect. And you have to be aware of hardware requirements, right? How expensive is the hardware? How available is the hardware if it's required? Can we just do it in software? And compatibility. Can we just run our existing workload, plop it in this new system? Do we have to rewrite stuff, recompile stuff? Like, what are we looking at here? And so I'm going to try and talk about each of these kind of as we go through the different technologies. Because I don't think this is one of those things where like there's a one technology that makes sense for everybody. I think it's more about kind of understanding the spectrum of isolation controls and kind of what makes sense for every person. So I'm going to go through each of these and talk about a few open source technologies in each category that kind of illustrate what the categories do. So first we have application and service isolation. Namespaces, I think, is the most known of these. They kind of provide a different view of the operating system for each container. These are very commonly used. And there's namespaces for different levels of the stack, right? But they all kind of fit into the same kind of category. And this is part of the operating system kernel. Then we have C groups. These provide different views of like specific system resources, sort of like namespaces, but in a different, but like to different resources. There's seccomp, which kind of filters your system calls. And so you can limit which system calls a particular container can access. This is super helpful because a lot of privilege escalation attacks require access to certain powerful system calls. So if you can just block those off, you kind of block out whole categories of attacks. This similarly runs in the kernel. I just kind of illustrated it above the kernel. Then we have capabilities, which define, instead of giving a container like entire root level privileges just because you need to do one thing, capabilities give you kind of more granular access to give containers access to specific capabilities that they need. And finally, we have technologies for mandatory access control, where you can set a policy for each container about what they're allowed to access within the kernel. And that was kind of a very quick overview of all of those. There's a lot more detail about all of them. But the main point here is that there's a lot of really cool features within the Linux kernel itself that provide isolation for your containers. The containers still have a shared kernel. They still share the user, like the memory and stuff like that. But if you layer all these together and you configure them correctly, you actually block some system calls, you actually do all that stuff, you can get some pretty powerful protections. But because these are all in the Linux kernel, this is where those kind of container escape CVEs from before come in, is that if there's some sort of issue in the Linux kernel, which is this huge piece of code, very impressive huge piece of code, sometimes it can affect some of these technologies in there, and attackers can get around them. So this is like a great kind of baseline. This is the kind of isolation everybody should be doing, right? It's the stuff in the Linux kernel, super compatible with what you're doing today. But for kind of more, when you need a little bit more isolation, we're going to get into some of the other options for how to get that. Next, we have runtime isolation. The first one I'm going to talk about here is gvisor, which is a user-level kernel. That's what they call it. So it basically sits between. It still sits kind of on top of the kernel. It's in user space, but it does a lot more on top of it, right, than just having like a single layer of like filtering. It kind of runs this whole kind of mini kernel on top of, in user space on top of the kernel between that and your container, which provides a really powerful isolation boundary. And I think this one's kind of unique because it's still in user space, and so it's still very compatible with all kinds of hardware, all that kind of stuff, but it still provides that really kind of clean isolation boundary like what we're going to talk about next, which is hypervisors and virtual machines. So first I'll talk about virtual machines in abstract, trying to make sure we're all on the same page here. So basic idea of a virtual machine is that on top of your hardware, you run what's called a hypervisor and a virtual machine monitor. And what these do is they partition resources from the hardware to different guest operating systems. And so then you have a guest operating system which can run, you note I put application and not container right here. They can run applications inside of these guest operating systems. Traditional virtual machines are very heavyweight, right? You're running an entire guest operating system to run your own process. This is probably not the best solution here, right? And they're really designed more for things like testing code on different systems or like dual booting than it is for containers, the world of containers. Which is why people came up with this idea of micro VMs. The diagram looks a little bit similar. We add in a container runtime, which can orchestrate the containers. And these kernels, they got smaller in the diagram because they're now microkernels, right? They're just like slimmed down versions of the kernel that just to run containers, just to make this whole thing have less overhead. They're really designed for containers, and so have all kinds of features, especially things like faster startup time. You can run a lot of VMs on a system, depending on the exact technologies you choose. You can run hundreds of thousands on a single machine, versus when you're running a traditional virtual machine, that wouldn't make as much sense. Yeah, and it adds that container runtime. So I'm going to talk about each of the layers here and a couple technologies in them. There's a whole world of technologies in each of these so lots that I don't cover. But we're going to start at the bottom with the hypervisor level. And the reason, we'll get into why I'm talking about this, but there's kind of two big ones in this space, in the open source space, right? There's Zen and KVM. KVM is a type 2 hypervisor. It's a module on top of the Linux kernel that basically accesses what's called hardware virtualization extensions in CPUs, which allows kind of really fast partitioning of resources to different virtual machines. And why this is important is that KVM requires both CPUs that support hardware virtualization extensions, and more importantly, actual access to those virtualization extensions. This means if you're running in the cloud, you have to have pass-through of, so if you're in the cloud, you actually have a layer below this, right, where your cloud provider has their own hardware and a layer between it, and you have to make sure that that layer between is passing through access to those hardware virtualization extensions. So you need like kind of bare metal type instances. Zen is another hypervisor. It's a type 1 hypervisor that sits directly on hardware, like not built on top of the Linux kernel. And it has this option with what's called para-virtualization. And para-virtualization means that instead of requiring the CPU to pass through resources, what it does is it requires the operating system kernel to support what's called hypercalls which are basically just system calls, but for Zen. So it's system calls that Zen can use. And most existing versions of Linux, I think with like maybe one or two exceptions, you can just compile in this way. So it's supported like that, and it does this kind of like at the software level instead of requiring that hardware compatibility. So yeah, so I think that's basically what's there. And I think that's the layer that is least talked about in this space, because I think a lot of people just assume one or the other. But I think it's important to talk about what the differences are and why people make those choices. So on top of that, we have the virtual machine monitor, often called a VMM. This is what kind of assigns the CPU and memory to the different virtual machines. Kind of it passes through from the hypervisor, which controls all the hardware. It just kind of manages that layer. One of the big ones in the cloud space is called Firecracker. It's what AWS Lambda and Fargate run. It's a virtual machine monitor that's really optimized for fast startup times and container runtimes. Another big one is Cloud Hypervisor, also designed for container runtimes, slightly different performance characteristics, also a great one to check out in this virtual machine monitor space. Then we have the container runtime. So unlike in the world of traditional VMs, right, we want containers to run inside of our virtual machines, and so which means we need a container runtime. Kata Containers is a big open source one that does this, right? It orchestrates the containers for the VM world, for the micro VM world. And then one more thing I'm going to talk about in this space is the unikernel. Again, you notice these are apps and not containers on this slide. That's because the unikernel has a slightly different model and a slightly different trade-off, which I think is interesting and worth talking about, right? So all of these diagrams before have a lot more layers. What unikernels do instead is they have you recompile your application with a slimmed down, specialized mini kernel. So what you get is kind of a single application mini operating system that you run that runs your application. This removes a lot of the overhead of these virtual machine systems while still getting all that great, really clean isolation boundaries. But it does require you recompiling your application, for each system every time you're using it. And so this works better for when performance really matters and for very specialized type systems. But I think it's worth talking about because it does kind of solve some of the performance stuff that people talk about in the micro VM space. So as a summary, mostly except gvisor, these have a separate kernel per container. And this provides a very clean isolation boundary, right? So you don't have a shared operating system anymore, no shared memory, which means that an attacker, if they're able to get out of the container, they just see an operating system that's only running their container, right? That's not that useful as an attacker. And so this provides a very clean isolation boundary. Unfortunately, some of these technologies have some additional overhead or some compatibility issues with your existing containers. And so that's just something to consider, and it's great for when you need that extra level of isolation. And occasionally, depending on the hypervisor level, there are some hardware requirements. How am I doing on time? Great. This one I'll talk about really fast, node isolation. It's more of an architecture than it is a technology, I would say. Basically, so what this diagram doesn't show you, and all my diagrams don't show you, there's, of course, there's more stuff between the container and the kernel, right? There are pods, there are nodes, all that stuff. And the idea here basically is that you can just put your whole cluster on one machine. And if you put your whole cluster on one machine, it's isolated from all the other clusters. And you can just put one container in that cluster. This gives you isolation, right? This is great. You lose a lot of the benefits of containers when you do this, but it's compatible with what you have. It totally works for this isolation. And I think it's worth mentioning because it's really easy to do, right? You can just architect it. So I don't like to discount that sort of thing. But then finally, I'm going to talk a bit about hardware and physical isolation, which means I get to talk about confidential computing. So confidential computing is this, I don't know what you call it, this technology. It uses this piece of hardware called a TEE, a trusted execution environment, that kind of sits next to or on the CPU. And it provides encrypted memory, which is really, really cool, because what it means is that your application and all your data can be encrypted not only at rest, not only in transit, but also actually in memory on the system, which means that even someone who has physical access to the hardware that your stuff is running on can't see what's happening inside the TEE, which is super, super cool. This usually works in the world of containers on top of some sort of virtual machine, micro VM type system, where you put that, you kind of put your guest OS in the container inside this TEE, and the rest of the infrastructure runs separately. What's cool about this is that you don't have to trust any of the stuff in pink in the diagram, right? You don't even have to trust your cloud provider, because you can get this cryptographic verification of the hardware itself running your application. The downside is that you need the hardware, right? And so because this is dedicated hardware for your application, you can't run that many containers inside a single TEE. All of this depends on the exact hardware model that you use, but they all have very, very small limits, and can be more expensive. And yeah, so that's an obvious downside to this approach. But for really, really critical, very isolated type stuff, this is a great standard. So for a summary of the first half of this talk, we have a bunch of isolation mechanisms. Application and service isolation in the user space level provides kind of a basic sandbox around your application. We have runtime isolation that operates kind of one layer down, mostly at the hypervisor level. We have node isolation, which is more of just an architecture decision. And we have this hardware and physical isolation, things like confidential computing. And I didn't have a slide for air gaps, but that obviously also fits into this hardware thing. We just put it on a whole separate computer that's not connected to the internet. That's a very secure way to go. So that's what we have here. And now, it's 2025, so I had to add this slide. And when I say AI in isolation, what I actually mean is GPUs in isolation, right? So that's what we're going to talk about here. And there's been a bunch of AI content already today, so I won't explain too much why I'm talking about GPUs. But as I'm sure most of you know, these AI models that are gaining prominence use GPUs in two main places. They use them both for training. And this is mostly done by the big companies that make the models themselves, lots of training. Some people do retraining of models on GPUs. But more importantly, I think for this talk, people use GPUs for inference, which means when you're using the models, you need access to a GPU to then run it on your query. Say you're trying to ask what color the sky is to this, because you don't know, to your AI agent. It needs to have access to a GPU in order to run inference on that. And GPUs are expensive, as I'm sure folks are aware. And so similar to when we were talking about containers earlier, you don't want to have to buy a whole computer to run your run application. You also don't want to have to buy a whole GPU just to run inference once a week on your stuff, right? So what you want to do is to let multiple different containers access the same GPU. And GPUs, it's really interesting, and I won't go too much into this, but they are architected a little bit differently than CPUs. And so the way that you do time sharing on CPUs, I think, is a well-established process, right, where you have one application access the CPU and then give it to another. This works a lot differently on GPUs because of the way so many different cores work together and the way that it doesn't by default always clear the memory in the GPU itself between different users, right? So you have to be really careful about sharing a GPU between different applications. for all those reasons. So there's, I kind of split these into 4 categories. GPUs, I think, really even more so than confidential computing, it just depends on which GPU you buy. And so this is kind of a generalization, but which of these are available to you just depends on which GPUs you have access to, and in some cases, which licenses on top of those GPUs you pay for. But anyway, so we have 4 different opportunities here. So we have the NVIDIA multi-process service. This one, I think, doesn't really provide isolation. That's not really the point. What it does is cooperative multi-process for CUDA applications, which I mentioned because it still allows multiple different containers to access the same GPU, but in this case, it's doing so cooperatively. So if you have different containers kind of working on the same application, this is a cool kind of software level interface for them to work together. Then we have technologies for GPU time sharing. This is, I think, more like the CPU level time sharing a little bit, in that it's in software and you kind of context switch between different containers accessing the same GPU. But again, some of the security and isolation properties of GPUs are different, and so these don't provide as strong of isolation, especially with things like memory. Like sometimes memory will be left over between the different applications that switch into the GPU. 2 technologies here that I'll mention is NVIDIA vGPU and I think it's Intel GVTG, which are both just different versions that do this kind of time sharing type technology. And then you can go down further into the hardware. These are kind of in rough technology stack order, and do GPU partitioning. So certain GPUs support this idea of splitting the GPU itself at the hardware level into slices, and then you can give one of those slices to each of your containers. I do think that you need to have them in virtual machines for this to work. So you have to be using some of that micro VM technology we talked about before. Two big ones that do GPU partitioning are MIG, which is NVIDIA's, I'm forgetting the I, it's multi-something GPU. And then the MX GPU, which is the AMD version that does something very similar. And finally, there's PCI pass-through, which gives a VM direct access to one GPU. Now, you're not sharing the GPU, except that you can, I guess, move its access somewhere else later. But this does give you much better isolation, right? Because of all those factors about GPU memory sharing and stuff like that, and also because some of the other technologies require some big licenses, like vGPU. There's a special license you have to buy from NVIDIA to use it. PCI pass-through doesn't have that, right? You just give direct access to your VMs to a GPU. It's still technically sharing because you can then swap the GPU from one VM to another, but it's not quite as clean as like the GPU partitioning. And so in terms of isolation, as kind of a summary of all the stuff I just said, this is the one slide to remember from this, is that we have stuff that's in software, which is the multi-process service. That one's not really for isolation. It's more for sharing the GPU, versus time sharing, which is more about like software-based isolation between different pieces of the GPU. And there's some performance impact for that because it's running in software, which can be a factor. And then we have GPU partitioning and PCI pass-through, which if your GPU supports them, provide this kind of more hardware-level isolation for GPUs. So yeah, that's what we have. We now have a GPU that can be shared among all our different containers. And I think this is a really important one to kind of follow, and I think there'll be more technologies coming in this space, because as more people are using GPUs for inference, as this space really grows, we need, I think, more solutions in this space for getting really good isolation. Like we have all those technologies in the existing container space for isolation. I think we're going to need a whole host of them as well for different levels of isolation in the GPU space. So I think this is going to be a really exciting next place to look. And I think also standards for the different GPUs so that you can actually have the same technologies, even if you can't always buy the same GPUs. But anyway, which I guess does lead me into my call to action. So kind of the reason I'm giving this is partly because I think it's interesting, and I hope that you think it's interesting, but also because I think it's something that we, as the cloud native community, should talk about more. And so this is my question for you, if you find me, is do you think about container isolation at all? What do you use to isolate your containers? And would you be interested in talking more about this in the context of the CNCF? And keep an eye out for some stuff in the CNCF tag security and compliance in this space. I think we're really looking to make some progress on this. So thank you all. We've got on time.